First speaker, Peter Palffy Muhoray, who I've had the pleasure of working with probably longer than just about anybody else, I think. It's a little worrisome to admit how long that's been. Rather than details of Peter, who I think all of you know, I'd just like to kind of point out the impact he's had on the Institute. He is kind of always looking for novel ways of working with liquid crystals, whether it's liquid crystal lasers, elastomers. It's been really key for the Institute as we strike out in new directions. And probably also most importantly, most of you in the room, at least that have been in the field for a while, have collaborated in one way or another with Peter. He's been great at building collaborations across the country and around the world, and has really left a big imprint on the Liquid Crystal Institute. And so it's my pleasure today to introduce Peter and have him present his talk on particle-shaped chirality and the optical response of bulk materials. Peter.
Thank you, John. Well, thank you for the kind introduction. It's a pleasure to be here. And I'll try to say a few fairly general and simple things, trying to relate particle-shaped chirality and the response of bulk materials. And my collaborators are Fred Minkowski, who's a student and related to the famous Minkowski. Not that Fred himself isn't famous. Epifanio Virga and Xiaoyu Zhong. So I want to say a few words about the aim of this exercise, and then talk about light propagation in chiral media, and then a few words about the packing of convex chiral bodies, and then I'll close with a very brief summary. So we were instructed to have fun, so I thought I would start with a joke. I'm not sure how to make that searching label disappear. So here it is. So in England, everything which is forbidden, which is not forbidden, is allowed. And this is, in fact, the constitutional principle of English law. In Germany, everything which is not allowed is forbidden. And in France, everything forbidden is allowed. So that's a joke. Now, something which is less of a joke is it has been proposed that the principle of totalitarianism is a system where everything which is not forbidden is compulsory. And this is a serious proposition. And now the relevant point is that there's a principle of physics which says that everything which is not forbidden is unavoidable. And this is a fact. There's no theorem, but anything which is not forbidden happens. And this, to some extent, is the main thrust of my talk. So the aim of this exercise is to think about chirality, which represents broken inversion symmetry, and to try to explore the connection between particle shape and macroscopic observables in systems of chiral particles. And observables are electric and magnetic properties, optical activity particularly. And of course, one can see acoustic activity just the same way. If you have transverse acoustic waves, shear waves, then you can see optical, rather acoustic rotation of the polarization direction in these systems as well. And then I want to say a few words about phase behavior. And what we would all like to do is to provide some measure of chirality, which I think is a pretty interesting concept. So I'm sure that everyone here knows the story of how Louis Pasteur separated right and left-handed crystals of tartaric acid. Essentially, he noticed that the crystals that were formed were geometrically different, and then he noticed that the optical rotation had a different sense, and so with tweezers he separated the two kinds of crystals. And so this was, I think, the first example of separating enantiomers. And this idea of crystallization taking place for pure enantiomers is actually rather rare. And so questions that come up then are, how does optical rotation come about? And why do enantiomers phase separate? And then what is the connection with the molecular shape? So these are the questions I'd like to not answer, but at least think about. So optical rotation. So before talking about optical rotation, I thought we'd have a quick demonstration of optical rotation. So Fred, please. So could we have the lights off? Could you hit the lights at the doors? Thank you. So there's a projector with two cross polarizers and a beaker in between. And if you look up by the ceiling, you can see that where there was no light being transmitted by the polarizers, now we have light going through. So that's a clear example of corn syrup rotating the plane of polarization as the light traverses the sample, and then it can now go through the second polarizer. And I'll try to extinguish it, Fred, if you would, by rotating the polarizer. And you can sort of extinguish it, but you can see that there's a wavelength dependence. So we can extinguish some colors, but not others. So very good, thank you. So this is just a brief demo in case you haven't been exposed to it. So the question is how to understand this. And we have, at least in this case, an isotropic homogeneous material. There are no net charges, so we have Maxwell's equation that describes what the fields are doing, and there are four fields that we typically talk about, E and B and H and D. And then where is the connection with the material? And the connection is through the constitutive equations, which originally were proposed to have this form. D is proportional to E, B is proportional to H. And so these describe the material response. So all the connection between the fields and the materials lives in the constitutive equations. And more explicitly, it's the electric polarization and the magnetization that really carry the information about the material response. So now I want to say a few words about linear response. So we like to operate, at least initially, in a world where systems are in a linear regime because it's hard enough to understand the linear response. And a nice elementary example is just an RC circuit, which is a linear circuit. That means that if I put in some input here, something will come out. And if I put in a second input, something else will come out. But if I put the two inputs in together, the sum of the two outputs will come out. That's what linear response means. And so this means that one way of predicting the output in general is to divide the input signal into little delta functions, look at the output, which comes out in response to a delta function, which you can call the Green's function if you're a mathematician. And then one adds up all the little Green's functions that come out due to all the little delta functions of the input. And in real space, we have that the output is a convolution of the system response and the input. And that means that if we take the Fourier transform, it is in Fourier space that we see that the output is proportional to the input. And the consequence of that here, of course, is that D equals epsilon E is valid only in Fourier space. And so I think that this is the important point I want to make, that epsilon, that this relationship really only holds in Fourier space. And even in Fourier space, it only holds if the system has homogeneity. That is, we have translational invariance in time. It doesn't matter when I put in my delta function, the system output will be the same. Only difference will be is that if I put in the input delta function later, the output will come out later. And this is not true if the system is not homogeneous in time. That is to say, if my R and C vary in time, then my Green's function is going to vary in time, and this simple relation will no longer be so simple. Okay, so optical rotation, how to understand it. So we know that d equals epsilon in Fourier space, and now we know that epsilon has to depend on k and omega. And if we want to include that dependence explicitly, the first non-trivial thing we can do is expand epsilon in a series in k, and epsilon is a second-rank tensor, so we get we have an isotropic system, so we have some constant times the identity, and then we have to have a term which is linear in k. If it's linear in k, then I have to have a third-rank tensor preceding it, so the product is a second-rank tensor. Only tensor we have is a Levi-Civita. We have no vectors, we have no anisotropy in the system. The only isotropic third-rank tensor we have is a Levi-Civita, which is just another way of talking about the cross product. And the thing about the Levi-Civita is that it's a pseudo-tensor. I mean, everyone knows, I guess, the world is divided into proper tensors and scalars and vectors and improper ones. It's sort of like there are real people and there are vampires. And the way to tell them apart is to look at them in a mirror, and you see that there's a difference. Anyway,
excuse me.
Yes?
Upper left, we cannot see something behind.
I am really sorry. I wish I could help, but I think we don't have it on this screen. I don't think it's a problem of my computer. I'm sorry, I cannot help.
There are some empty chairs here, so this screen is better.
All right, so the point is that because we have a pseudo tensor here, epsilon must be real, so I have to make epsilon, so epsilon must be proper, so I have to turn this into a proper quantity, and I can only do that by multiplying it with a pseudo scalar. So two wrongs do make a right in this case. Okay, so the point is that for this term to be allowed, I have to have a pseudo scalar, and as you all know, a pseudo scalar is a scalar that changes sign under inversion. And one simple way to make a pseudo scalar is to take the cross product of two proper vectors and then dot it with a third vector. Then you have a scalar that has this property that it changes sign under inversion. Now, if we just take this simple expression and stick it into the wave equation, the solution pops out immediately. It's two circularly polarized modes with opposite handedness propagating at different speeds, which is optical rotation, and one can relate the optical rotatory power, this coefficient, to this pseudo scalar here in gamma. So the punchline really is that the story is really simple. So long as we have a pseudo scalar in the system is chiral, and it will show optical activity. Of course, the question is, where does this gamma come from, and how big is it? So now, one can, of course, write this relationship in real space, and if you stick that into the expression for D, you can write it as the curl of E. So this new term is the curl of E, and you can write that, because of Maxwell's equations, in terms of the time derivative of B. So if we allow spatial dependence of epsilon through k, then at least at this level, that's equivalent to writing the constitutive equation for D as introducing a new term, which is either proportional to the curl of E or to the time derivative of B. And there are two schools of thought on this. There's Landau and Lifshitz, and Casimir and Agranovich, and I particularly stress Agranovich's work, who focus on spatial dispersion, working in Fourier space, and the other school, the Drude-Born-Fedorov school, who look at non-locality in real space and essentially write things in terms of the curl of E. And these two approaches have been reconciled, but questions remain. And I really briefly, yeah, so these are the two sort of formalisms working in Fourier space, and this is the so-called bi-anisotropic description, because in principle you can have two tensors in the case that the system is anisotropic. So we did some numerical experiments a while ago, not to probe chirality, but just to probe the descriptions of non-locality. So imagine two gold nanoparticles, ellipsoidal, different in size, separated in space, and then sending in fields with various configurations. So blue is the electric field, red is the magnetic field. Now, I don't know why the color is not coming through very beautifully. In any case, if you consider driving this system with orthogonal E and B fields propagating in different directions, you get some rules about the induced dipole moment. And it turns out that if you form these sums, then bi-anisotropy predicts that they should add to 0. And we did numerical simulations using Microwave Studio and discrete dipole approximation. And what one finds is that there are pretty significant deviations from the predictions of bi-anisotropic description. On the other hand, the Fourier space description, the spatial dispersion description gives really good agreement with simulation. So here we are plotting this general normalized sum as a function of the wave vector times the separation between the particles. So the only point here I want to make is that the bi-anisotropic description doesn't seem to agree well with numerics, whereas the spatial dispersion picture does much better. So we are kind of prejudiced towards the Agranovich description. So now everything we said so far had assumed spatial homogeneity. I'm going the wrong way. And the main point is that these nanoparticle systems are not spatially homogeneous. So, yes. Thank you. Not spatially homogeneous. And I think that that's a really formidable challenge to formulating an accurate description. All right. I want to turn now to particle shape and chirality. And one can make a really simple model. Imagine that you have just a line with 3 polarizable wires on it, and they're rotating, as you can see, in space. Now, the interesting thing about this thing is that it's chiral, but there's no vector associated with it. If I turn it upside down, it's just the same as before. So it lacks inversion symmetry, but it's not polar. And one can write down the polarizability of such a thing, and it looks maybe a little complicated. But the main point is that because of the angle between these polarizable bits, one ends up with a cross product in describing the orientation of the wires, and that cross product has to be preceded by a pseudoscalar. And now if one actually calculates the polarizability, one can get a number here. Okay, so this is just a geometrical figure. This is the inverse pitch, essentially tells you how big the angle changes. And then one gets other numbers just from considering the physical polarizability. And so the point is that if one writes, if one looks explicitly at this structure, one can write D in terms of E, and one can see explicitly how the pseudoscalar originates and where the pieces come from. And so that basically answers the question of where gamma comes from and even how big it is. So this is something that one could, in principle, evaluate. Okay, of course, one can look at solid bodies which are chiral, and Fred whittled a few convex ellipsoids which are chiral, and one is left and one is right-handed. So, and in this case also, one has to have a pseudoscalar, and it seems that both in this sort of general geometric situation and in the polarizability, the pseudoscalar has the structure of inverse pitch, and then the volume of the object, and then some characteristic length squared in the denominator. Now there are other sources of the pseudoscalar. In V-shaped molecules, we have a number of anisotropic quantities. Pneumatics have a director, but there's no arrowhead, so it's a dyad. Smectics have a layer normal. Also, there's no distinction between up and down. And we have electric polarization, because these molecules are polar. And one can form a pseudoscalar from these quantities, and the system necessarily becomes chiral, and the optical activity has been demonstrated very beautifully by Tony and Oleg's group. So this is just an example where the chirality doesn't come obviously from a structural element of the constituents. Now, phase behavior. So attractive and repulsive interactions play a role typically. And so in the free energy, we have two terms. There's a term with the attractive energy that you're familiar with and the repulsive part. And I want to focus on the repulsive part for a minute. And the excluded volume is a key quantity here. And that's essentially the volume that one particle makes inaccessible to the center of a second one. And Bela-Mulder showed really beautifully that the excluded volume of particles A and B can be thought of as the Minkowski sum of particle A and the central inversion of particle B. And it turns out that based on this idea, we were able to show the following theorem. Suppose you have a convex body, and somebody gives you plasticine, a deformable body of a given volume, and they ask the question, what should be the shape of the deformable body so that the excluded volume between the given body and the plasticine ends up being a minimum? And the answer to that is that the shape of the deformable body that minimizes the excluded volume should be the central inverted version of the original one. So in the case of convex chiral bodies, this means that left and right-handed enantiomers pack better. And so entropy likes things to mix, but this packing result means they like to make things mix even better. So why should it be that these crystals that Pasteur found separated into left and right-handed enantiomers? And there's two possibilities. One is that the bodies are not convex, the theorem doesn't hold. The alternative is that it's energetic, that the attractive part of the energy is responsible. And one could look at the energy as well. Typical London dispersion has the form of the product of the polarizabilities. And I don't have time to really dwell on this, but the point is that we can assume that the polarizabilities have this form where we have some tensor and other piece which is multiplied by the pseudo-scalar that I've been talking about. And then one can look at the interaction between left and left-handed enantiomers, right and right, and left and right. And this elementary argument shows that the interaction between left and right, at least in this case, shows that the same kind of enantiomers attract each other more, and that's sort of consistent with what's observed. This is a really naive argument, though. Typically, one doesn't have the spatial averaging that I assume to get here. So the converse may also be true for special orientations of the enantiomers. So the only remaining mystery, at least to me, was then how come that the melting points cited on this page are different? And that's a real puzzle because everything is the same. And the answer to that puzzle is that this is just an error. More careful studies show that the melting points, in fact, are identical for left and right. OK, so that's the end of my story. I think the point I want to stress that if a pseudo-scalar is present in the system, then chirality is allowed. And if it's allowed, you will have it. I think modeling this accurately is a real challenge. And I think because of non-local response, spatial inhomogeneity and the boundary conditions. And I think that this is one area where we can really use some help from applied mathematicians. I think the spatial dispersion model is preferable based on our limited but interesting numerical results. And convex enantiomers of opposite-handedness pack better. Thank you.
Peter, we have time for a few questions. Jonathan?
So Peter, in the first part of your talk about the electromagnetics, was that entirely concerned with isotropic distributions? I lost track of that, right? So certainly in the demo with the sugar solution, that's isotropic.
That's right.
And your vector calculation with Maxwell's equations, that's for isotropic material.
But the notion that D is a function of K, and then expanding that in general with tensor coefficients, yeah, that works for anisotropic materials just as well.
So I guess with the numerics, just to double check, but the numerics, is that also for an isotropic distribution of orientations of the body?
No, the numerics was for the two ellipsoidal gold nanorods, as I have shown, and there's no change in their position. So we're just sending in different plane waves with the electric and B field in different orientations, and then we are calculating the numerics. The gold is isotropic, and we know how to calculate what happens inside the nanoparticles and calculate the dipole moment of the pair.
The ellipsoids, have some orientation.
Right. The ellipsoids, we only consider those two ellipsoids, and their orientation doesn't change. We ask the question, what is the induced dipole moment when those are hit by a plane wave coming from some direction?
Does vector depend on the orientation of the plane wave?
It did. Right.
It did.
The different P's were associated with different orientations and different polarization. Yeah, I'll be happy to show you. It went a little quickly. I'll be happy to show you the details.
So here's the question. Did Pasteur separate enantiomers or diastereomers?
I believe they were enantiomers. But I'm not certain.
Yeah.
Please.
Peter, hi. I am interested in the part when you mentioned that inhomogeneity of nanoparticle structures can translate into the nonlinear behavior, if I understand it correctly. The question, what I would like to ask is, what scale of inhomogeneity?
I think I meant non-linearity when you do the expansion in Fourier space, not in the sense of nonlinear optics of harmonic generation.
But still, what would be the scale of
well, when the inhomogeneity gets comparable to the wavelength, more or less.
So that means it's in hundreds of nanometer scale?
Yes, yes. But maybe more to the point is that to do the numerics properly, you have to, I think, average the Green's function over your unit cell. And so inhomogeneity in there will count essentially regardless of the wavelength.
Yes, I think that actually is something which I understand a little better, and I can connect it to the interface, because the particles are not uniform. So the assumption is typically made in physics that all that ellipsoid is made from the same, say, gold.
Right.
But it's actually not true. That interface, the atoms there do not have the same polarizability.
That's right,
as
the ones in the middle, yeah, that's right. But I think that dealing with the individual nanoparticles is relatively doable, even if you put in the surface layer correction. People have done that. I think the real issue is the non-locality, that if I induce a dipole moment in this guy, I will get dipole moments elsewhere as well. And I think that that's what's driving the chiral response in these chiral nanoparticle clusters.
Yeah, so it's a question about the scales. If you take this geometrical model of the chiral objects and then calculate the pitch of, let's say, cholesteric bracket, would you be getting anything different from the molecular scale or object scale like we see in natural cholesterics, or would it be something much larger or of the same order?
I'm sorry.
So you know that in cholesterics the pitch is much larger than the kind of molecular scale.
That's right.
If you take your model that is based on individual objects, will you be able to predict much larger pitch or not?
No, you will. Yeah, you will. You will. And I think Goossens has a model for interaction of chiral particles. And he basically has that, but of course determining exactly how big the pseudoscalar is in that potential is a challenging bit. But I think in principle you can.
But you have to do it in the right thermodynamic phase. If you do it in the biaxial phase, then you get a different answer than if you do it in the uniaxial. Right? Because the shapes that you have to rotate. If it's uniaxial, they can't have long rotation.
That's right. That certainly plays into it. Absolutely.
Well, this raises about 100 questions and comments. But one comment I'll make is that Pasteur was working basically on a problem that the French wine industry had when he discovered this resolution, number one. German wine industry? The other point is that, at normal room temperature, you always get the racemate crystal from sodium aluminum tartrate. But it was really cold and they had no heat in the lab. And so he got lucky and did the crystallization under conditions where he got the conglomerate. Then the other question I had was, has anybody actually measured the rotatory power, the actual rotatory power of a cholesteric? Because they have so much linear birefringence, it's hard to see the circular birefringence. So what is the rotatory power of a cholesteric, the circular birefringence?
You mean in the isotropic phase or in the helical phase?
In the cholesteric phase. you know, it should have some rotatory power, but I don't know if anybody's ever seen it or looked for it or if you could see it.
For twisted pneumatics, it's easy.
No, but that's, you're seeing linear birefringence, right? Optical activity is circular birefringence, which is orders of magnitude smaller than linear.
The normal modes in a cholesteric are essentially elliptically polarized modes, right?
The molecules are chiral. Yeah, there's no
Right.
spontaneous cholesteric. So you would be seeing the rotatory power of molecules.
Well, you see that in the isotropic phase. I think in the cholesteric, you really see a combination of the spatially varying linear birefringence, as you say. But epsilon doesn't care about that. Epsilon just says this is what it is.
But it's so much smaller, it's very hard to observe.
That's right.
So that's an interesting question if you have a cholesteric versus molecules in solution. The same molecules in solution will give some circular birefringence. So then you stick them in a cholesteric, it should be different. But I don't know if anybody's ever looked at it or looked for it, because it's so hard to see this tiny circular birefringence when you got this enormous linear birefringence.
Well, so Dave, would that be the same as taking the cholesteric and averaging over all the directions of propagation for the light?
Well, I mean, I'm talking about experimental nature. I don't know. You can't take molecules in solution, you have to circular birefringence and then extrapolate that to a cholesteric.
The linear ones don't cancel.
Because the conformational picture is well, you just look in the isotropic, you can see the rotatory.
When you put it down, it has CD weird labels.
So that gives you the circular birefringence of the cholesteric. Because the molecules in the neat cholesteric are not the same as the molecules in solution, are they?
Right,
So,
what you're saying.
we're going to continue this. And move on to our next topic. First, thank Peter for an excellent presentation.